And the next talk will be given by Guide on opportunities for linear algebraic graph databases.
Okay, good afternoon. My name is Guy from Carnegie Mellon Universities. In this work, I am working along with Upasana Sita and Professor Seming Lo on opportunities for linear algebraic graph databases. First, let me start by describing what are graph databases. A graph database is a storage system that uses graph structures with nodes and edges to represent data. Users can provide queries, for example, finding all triangle patterns in the graph data. And then the system will compile and process the queries to retrieve data wanted by the users. The query job ends after the data is delivered to the users. Graph databases use graph algorithms, for example, subgraph matching and graph traversal to process queries. GraphBLAS, a standardized API based on the language of linear algebra, allows for a separation of concerns between graph algorithm designers and library developers. So by expressing graph algorithms using GraphBLAS API, graph algorithms designers can focus on the development of the algorithms without concerning performance-driven details. On the other hand, we have library developers that, by GraphBLAS API, they can focus on delivering performance for a specific set of APIs. And with high-performance libraries of GraphBLAS and the graph algorithms represented using GraphBLAS API, high-performance implementations of graph algorithms can be attained. And in the domain of graph databases, Redis Graph is a graph database adopting the GraphBLAS approach for implementing the graph algorithms. In this talk, I would like to address two challenges for using GraphBLAS in the domain of graph databases. The first challenge is about multiple data representations, and the second challenge is about multiple GraphBLAS operations for representing field operations. Well, let's start with the first challenge. To give you an idea of how data are represented using GraphBLAS, let's look at the following tables. For graphs, we know that we can visually represent nodes as a circle, in which inside of the circle we can represent node identifiers. For graph databases, we can represent a set of nodes as a node list. For GraphBLAS, we can represent a set of nodes as a node matrix, where each row in the node matrix represents a node identifiers by its non-zero index. For edges, we can visually represent edges as a link between nodes. For graph databases, we can represent edges, a set of edges, as an edge list. And for GraphBLAS, we can represent a set of edges as an adjacency matrix. To illustrate the problem, let's look at the algorithms for finding triangles in the graph databases, in which the idea is to iteratively construct triangles starting from a single node in the graph. The first step is to list all the nodes by read all the nodes from a list in the graph database. And then each node will expand itself by traversing into its neighborhood and add them as the next node. This will create a list of two-node walks. Then we need to make sure that the first and the second node of the walk are not the same, because we don't want the first and the second node of the triangle to be the same nodes. So we do filterings. And then we iteratively go through traverse and filters to generate a list of 3 nodes walks, a list of 4 node walks, and then coming back to a list of triangles. And people in GraphBLAS communities recognize that traversal can be represented using matrix multiplication. Let's see how. So we're going to zoom into the traverse A to B stage. And let's assume that the first stage, which is the read all node stage, is represented in the graph database representations. So we're going to get a list of nodes. Then we convert the list of nodes as a node matrix to use GraphBLAS. After we multiply the node matrix here with an adjacency matrix, we're going to get a result matrix in which each row represents a neighborhood of a node in the node list. And after we multiply all the rows in the node matrix with an adjacency matrix, we're going to get the result matrix that represents all neighborhoods of all nodes in the node list. But before we proceeding to the filter stage, which is assumingly not represented in GraphBLAS, we need to generate a list of two-node walks. And to generate, we take neighborhoods from the result matrix. For example, the first row of the result matrix here represents a neighborhood of node zeros, which is the first node in the node list. It consists of nodes 1 and node 4, in which we can visually represent it as a walk from node 0 to 1 and node 0 to 4. And based on this semantics, we can generate a list of two-node walks accordingly. So the previous example showed that we need to convert from GraphBLAS representations to the graph database representation, in which the conversion are not free. It costs us time and space. So how should we mitigate it? The idea is the unified data representations in linear algebra, which is to represent all operations as much as possible in linear algebra, so that we don't need to convert from one representation to another representations. And people recognize that the filtering stage here actually can be represented using an element-wise matrix multiplication. Let's take a look at the previous example. Focus on the third rows of the result matrix, which represent a neighborhood of node 3, which is the third node in the node list. In which, in this row, it contains nodes 1 and node 3, which it can be, we can represent it in the node list as a walk from 3 to 1 and 3 to 3. And we know that walk from 3 to 3 going to be removed in the filtering stage. So the idea is to remove node 3 from the third row of the result matrix. By doing that, we can create a filtering mask that in the third row and the index number 3 is the only zero element. So if we can apply element-wise matrix logical AND between the previous result matrix and the filtering matrix, we're going to get the result matrix that in the third row we don't have node 3 anymore. And that is the first challenge and how we overcome it. Next, we're going to talk about the next challenge, which is the multiple GraphBLAS operations for representing fuse operations. But first, what should we fuse operations? Let's consider the first traverse and filter stage. The traverse stage is going to produce the traversal output. And the filter stage will take the traversal output and then create a filtered output, in which it is a subset of the traversal output. So the traversal output here tends to create a larger intermediate data than the filtered output, in which it's going to cost us more space. Moreover, since if we separate traverse and filter stage out from each other, we need to firstly fully materialize the traversal output first, in which we can lose an opportunity to utilize localities in the filter stage. By fusing both traverse and filter stages, it helps us reduce intermediate data as well as increase in opportunities for better utilized localities. And there exists a knowledge for fusing traverse and filters by using mask matrix multiplication in the GraphBLAS API. So the mask matrix multiplication with a write mask that selectively writes elements onto the result matrix is up here in the GraphBLAS API. In this case, we generate a write mask using the node list. So the only filtered result will be written onto the result matrix. But this is not the only opportunities for fusing operations. There is an alternative approach for finding patterns. But why do we care about the alternative approach? I would like to talk about the problem of the previous approach, which is in the filtering A not equal to B not equal to C stage. It turns out that this stage will produce a list of 3-node walks, in which our last stage here will produce a list of 3-node cycle that is actually a subset of the list of 3-node walks. And since the larger list of walk is generated, this is going to cost us both space and time to maintain it until we reach the final stage. The alternative approach I would like to suggest is called common neighbors identification, which is to find common neighbors of multiple nodes. For the triangle example, after the first filtering step, now we're going to have all the information for the first and the second node of the triangles. And it turns out that the third node of the triangle is actually the common neighbors between the first and the second nodes. So if we can find the common neighbors between node A, the first node, and the second nodes, to find the third node, we can form a full triangle without the necessity to find a list of 3 node walks and a list of 4 node walks. To represent it in GraphBLAS, we recognize that the common neighbors identification can be viewed as a 2-step approach. The first step is to extract relevant neighborhoods, in which it is to extract the first and the second node's neighborhood. And the second step is the intersections between the first and the second node's neighborhoods to find the common neighbors that represent the third node of the triangle. For the first step, which is to extract all neighborhoods, it can be done using matrix multiplications. So we can start by taking the previous state result, which is the result of the first filtering stage, in which we're going to get a list of 2 node walks. And then for each walk, we can represent each node as a different rows in a different node matrix, using the same approach as we used before. And then we can extract the neighborhoods using matrix multiplication with an adjacency matrix. As a result, we're going to get the neighborhoods of the first and the second node of the triangles. After this, after we get both of the neighborhoods, we can apply an element-wise matrix logical AND between 2 of the result matrix. And finally, we will get the common neighbors between the first and the second nodes of the triangles. And know that it is possible to fuse with the filter stage, if you want, by introducing a right mask at this stage. As a result, common neighbors identifications can be represented as a multiple GraphBLAS operations, in which we can save both space and time. But why multiple operations? Can we fuse them, or can we do it better? Well, we start by taking the first attempt, since we recognize that both of the input matrices are going to be multiplied by the same adjacency matrix. So we start by fusing both of the matrix multiplication together. We merge both of the input matrices as a matrix SAB here, and note that we can directly generate this input matrix from the previous state result directly. We don't need to generate the first 2 input matrix on the left-hand side. And then after we multiply this input matrix with an adjacency matrix, we found that the result doesn't match with the common neighbors anymore. Well, let's consider the first dot product here. The result is 1, in which the common neighbors result that we want should be zeros. And this goes the same for the next 3 dot products, except for the last one. Our observations found that this matrix multiplication is the same as we apply element-wise logical OR between the first 2 row vectors of the adjacency matrix, in which our neighborhood intersections, use logical AND. And since GraphBLAS actually allows us to customize the operations, so we're trying to change from logical OR to logical AND. Now, let's consider the first 4 dot products based on the change of the operations. We found that the first 4 dot products here are now matched with the common neighbors result, except for the last one. And this is because in the last dot product here, the last 3 multiplications return zeros, in which these zeros will annihilate the first 2 multiplication result, in which we don't want it. So instead of we use logical AND as our multiplication in the dot product, we define a new multiplicative operators instead. The new multiply operators is represented as a truth table on the screen, in which we base on the logical AND operations. But if we can recognize that the elements on the left-hand side is zeros, we're going to return 1. And since 1, when we do apply logical AND with any elements, you will get the any element. So by giving this new multiply operations, we can now achieve the common neighbors result. And this is semantically the same as we applied element-wise logical AND between the first two rows. However, the problem is if we would like to implement these custom multiplications, we can get wrong results using GraphBLAS libraries. And this is basically because it doesn't fulfill the GraphBLAS assumption. But there's still an opportunity since we can use the same access patterns as a matrix multiplication to implement our third attempt. So we're trying to do it. And that is our two challenges for using GraphBLAS in the graph databases. The first one represents an opportunity for having a unified data representations to achieve better performance. For the second challenge, represents that we can use the same data access patterns to represent a single matrix multiplication for representing the fuse operations. And we implement all the solutions or all the opportunities for each challenge in the open source system called Redis Graph. First, we experiment them with the triangle finding queries in the CIT patterns graph. The plot I am going to show you contains y-axis, which is runtime in milliseconds, and the x-axis will be different implementations. For each bar, it's going to contain 4 stacks. The first stacks represent runtimes for the read-only stage, which is the first stage. And the second stack represents a runtime for the traverse, or if we have fuse operation, it's going to be a runtime for the fuse operations. The third stack represents a runtime for the feeder stage. And the fourth stack represents runtime for the Redis graph output, in which it is a stage that we're going to take the last state result and convert it into a user-desired format based on the query they provide. From the baseline, after we introduce the fuse traverse and feeder stage, we gain 1.32 times speed up. After we introduce the common neighbors traverse, we gain 6.37 speed up relative to the baseline. But this is only when we use only GraphBLAS. So we do it further. After we relax the GraphBLAS assumption, we gain 10.14 times speed up relative to the baseline. And finally, now all the operations in our pipeline is represented in linear algebra, except for the first read-only stage and the output stage. So we can remove the conversions between them, in which after we remove it, we gain 14.82 times speed up relative to the baseline. We also experimented with more workloads and graphs by using 3 implementations, which are the baseline implementations, the implementation in GraphBLAS, and the implementations that we went beyond GraphBLAS. Those workloads include 10 query patterns. The y-axis of the plot is going to show you a runtime in milliseconds, as well as in the log 10 scale. If there is no bar, it means that it times out at 1,000 seconds, or around 16 minutes. And the x-axis I'm going to show you will illustrate different graphs. For each graph, there are at most 10 queries, as shown on the screen. And for each query pattern, there can be at most 3 bars, representing different implementations. And the results show that our implementations are faster than the other 2 implementations, and this goes for other workloads and graphs. Well, in conclusion, this work shows you an opportunities for leveraging linear algebra in the domain of graph databases. The first one is we observe that many graph database operations can be represented in linear algebra, and if we can represent it, we can reduce the conversion cost between the graph database operations. The second point is that with GraphBLAS API, we can fuse multiple operations in which it can save us both space and time. And third, by relaxing the GraphBLAS assumption, more operations can be fused, as I show you in the example of the common neighbors identification. And that should conclude the talk.
Thanks for the talk. That custom multiplication operator you came up with, isn't that Boolean logical implication?
So, you mean this one, right?
Yeah, isn't that just logical implication? That's how you write it. Yeah, it is right. So can this be understood? Is there any correlation between logical implication and edge finding, or is it just a coincidence? After all, there are only that many binary logical functions. Does it have any relationship to logic?
So can you repeat the questions again?
So this operator is usually written as implication, it's logical implication, or less than or equal, will be another way of looking at it. Is there any connection between the kind of what we think about as logical implication and what's actually going on here, or is it just a coincidence that the truth tables are the same?
Okay. I actually haven't thought about it before. That it is very similar to the logical implication that you say. Well, I don't think I can say anything about it. I need to take more time and think about it more. Yeah, but it is actually, similar to what you say, the logical implications. Thanks.
So I have a question. So just to follow up. So I guess the idea, the point here is that it's not commutative, but it's associative, right? So
Yes.
so you need to have a special operation.
Yep.
Another question on: is it possible to extend this to also do queries where you are looking for regular structures, like maybe you have a clean star, you want to say that there's somehow that you reach someone, or there are cycles, you can look for those things, or are they have to be fixed? In the examples you show, I guess there are no like arbitrary paths. You just have to say that they have to be kind of fixed, the structures. Would it extend to having
like
closeness of the somehow closeness properties?
For the common neighbors identifications, or like the basic one. So, as I understand your questions, correct me if I'm wrong. You are asking me that is my approach can be applicable with like the kind of patterns that have a closeness structures, like a loop, those kind of thing.
Yes. So maybe you want to find whether there are any islands, or someone who is not connected, who are only connected to one other person, or something like that. So that might be, you might have multiple paths before you actually reach, but you don't know how many.
The query that I don't know how many hops I'm gonna traverse, right?
I was just thinking that there could be such queries could exist. I'm not familiar with it. I was just.
I think in the domain of graph database we have a queries like we have like a star queries that we can have like any hops as much as possible. Actually, the common neighbors identification one, I don't think it is applicable with it can be directly applicable with that multiple hops things. But for the first opportunities, which is the unified data representations, I think that can help improve the performance, right? Because in the common neighbors identifications, as you say, we need like some kind of a loop patterns in order to like identify, in order to take an advantage of using like common neighbors to identify the next node, right? Is that clear for you?
Yeah, so I guess you can fuse certain parts, and then you need to, at least you can use those and fuse those and get optimized. Yeah.
Yep.
Other questions? Okay.
All right.
Let's thank.
Thank you.